If you look closely at the atomic structure of a standard copper wire, you will see electrons buzzing frantically, but they aren't going anywhere. This random, chaotic motion yields no net movement. To harness electricity, we need an organized flow. We define electric current formally as the rate of flow of electric charge. Mathematically, it is expressed as I equals Q over T, where a specific amount of charge crosses a boundary in a given unit of time. Think of the copper wire as a perfectly horizontal pipe filled with water. The water sits completely still. It requires an external force. Connect that pipe to an elevated tank, and the pressure difference forces the water to flow rapidly out the other side. Current is merely an effect. To organize the chaotic electrons into a measurable flow, we must introduce a specific driving cause. The driving force is an electrical pressure difference. In physics, we call this potential difference, or voltage. Potential difference is mathematically defined as the exact amount of work done to move a unit of charge between 2 points. The equation is V equals W over Q. In a typical circuit, a battery or cell performs this job. It expends its stored chemical energy to generate and maintain a constant pressure difference across its 2 terminals. Our objective is to find the exact mathematical relationship between this electrical pressure, the resulting flow of charge, and the physical materials carrying it. Analogies are useful, but physics requires replacing them with hard numbers. Understanding this precise math is the only way we can reliably predict and control electricity. In 1827, German physicist Georg Simon Ohm set out to map the relationship between voltage and current. This diagram shows a recreation of Ohm's experimental setup. It consists of a nichrome wire, an ammeter connected in series to measure the current, a voltmeter connected in parallel to measure the potential difference, and a single-cell power source. If we add a second cell to the circuit, we double the potential difference. Instantly, the reading on the ammeter rises in exact lockstep. Every time the voltage is increased, the current increases by the exact same proportion. This graph shows the result of those readings plotted against each other. The data points form a perfectly straight, upward-sloping line, proving a direct proportional relationship between voltage and current. The slope of this perfectly straight line represents a mathematical constant for the given wire. We call this constant resistance, denoted by the letter R. This finalizes Ohm's law. V equals I times R. Resistance is the defining metric. It predicts exactly how much flow a specific electrical pressure will yield in a given circuit. Moving from the math back to the physical wire, we have to ask what atomic forces actually create this resistance to the charge. Electrons are not completely free to move. Their motion is constantly retarded by the attractive forces of atoms they must navigate through within the conductor. Let's set up a comparison. On top is a standard wire of length L and cross-sectional area A. On the bottom is a wire of the exact same material and area, but twice the length, 2L. Doubling the length means doubling the obstacles the electrons must pass through. This strictly cuts the electric current in half. Resistance is directly proportional to length. Swap that long wire for a thicker one, doubling the cross-sectional area to 2A. A larger cross-section offers a wider path for charges to flow. The ammeter spikes upward, showing resistance is inversely proportional to area. We can combine these 2 physical observations into a single geometric equation. Resistance is proportional to length divided by area. Resistance is inherently structural. If you change the physical dimensions of the conductor, you permanently alter the math of your circuit. This leaves one final variable. What if 2 wires share the exact same length and thickness, but one is copper and the other is nichrome? To balance our equation, we introduce a constant of proportionality called resistivity, denoted by the Greek letter rho. This completes our formula. R equals rho times L over A. Resistivity is the inherent, unchangeable atomic fingerprint of a specific material, regardless of how it is shaped or cut. This chart displays the immense differences in this property. Silver sits at the extreme low end, making it an excellent conductor, while insulators like rubber and glass measure incredibly high, restricting flow almost entirely. We can engineer materials for specific purposes. Alloys like nichrome are designed to have a higher resistivity than pure metals, resisting oxidation at high temperatures. This property is what allowed engineers to turn electricity into controllable heat. This antique electric toaster utilizes highly resistive metal coils to deliberately slow the charge and convert electrical energy into thermal energy. Mastering resistivity allows us to intentionally design components to act either as invisible delivery highways or as deliberate consumers of energy. We can bring all these rules together by examining a complete system, multiple resistors joined end to end. This schematic shows three distinct resistors, R1, R2, and R3, in a single continuous loop with a battery. Because the path never branches, the current is absolutely identical everywhere. But the potential difference is not. The voltage drops independently across each resistance. The total work provided by the battery's chemical energy must be sequentially divided and completely expended across these three resistors. This gives us the governing law. The total potential difference exactly equals the sum of the individual voltage drops. A series circuit acts as a strict zero-sum system of energy distribution along a bottlenecked path. We can now combine this system-level observation with Ohm's law to calculate the total equivalent resistance of the entire circuit. We start with V equals V1 plus V2 plus V3. Substituting Ohm's law replaces every voltage term with I times R. Since current is constant, dividing the equation by I reveals the final equivalent resistance formula. Rs equals R1 plus R2 plus R3. The behavior of electricity is not random or chaotic. It is a strict, predictable negotiation between potential energy, charge flow, and physical space, all governed by foundational math.